Let's talk about unprotected mode. When we program in Windows or Linux, like the last time, in modern world, in modern operating systems, we take protected mode for granted. But everything has a context. Protected mode was introduced not from beginning in x86 architecture, but once it was introduced, it was hard not to use it because of many advantages that it provides. So let's take a look at as I said, unprotected mode, what was before it, and why protected mode is much better and why every operating system now uses protected mode. Or extensions of protected mode, like long mode is just a protected mode with additional features. So if any of you programmed in DOS, you may know that DOS operating system was a single task operating system, and this single task, a single program that was run, could take control of the computer completely, because there were no other programs running in background to need the resources even, except for some terminate and state resident programs, but that's another story. Any program in DOS was allowed to use all resources to its liking. It could use entire memory, it could use all devices directly. And the original mode of Intel processors was called RealAddressing Mode. This refers to the fact that addresses in this mode were directly corresponding to physical addresses in memory as on the board. And thus, in real mode, any program had access to physical memory directly, almost directly, and to entire physical memory. So something done in modern operating system in protected mode, this is something unthinkable, to give a normal program access to entire memory, because of course program may then overwrite some important sections of memory and break everything, even break functionalities that it depends on. Yeah, real mode had also some limitations related to 16-bit addressing. Let us start with some simple program, perhaps to show how the memory was accessed. Let's go with FASMD and write some simple program, COM program. Well, I would like to start with a simple experiment. Let's set up text mode. This is a classic text mode used by EGA, VGA. Well, originally CGA. It was perhaps first graphic card that introduced this color mode. Let's zero our DS register. We are going to access physical memory from the very beginning. Yes, I have not updated FASMD here in this DOSBox. I should update it later. It does not matter at this moment. I'm also setting up ES register to point to video memory so that we can write something on screen. We are going to copy some memory contents from physical memory at address 0 to video memory so that we can see in fact that it works and that we can see the context of the contents of this memory. If you do not know, text mode has a layout of 2 bytes per character. First byte is just a character directly, and second byte is so-called attribute. It consists of 2 4-bit nibbles. One nibble is the color of background and one nibble is color of text. We are going to prepare this attribute for now. 4 is dark red background, E should be yellow text. So we are going to copy contents of memory. So we are loading byte after byte, but we are storing words. So not only next to the byte we store additionally AH register, which is attribute, so color of text. And let's do this 80 times 25 times. At the end, let's wait for a keystroke. And as long as there is no key pressed, let's do this again. Otherwise, exit program. Let's try if it works. Save it somewhere here. Alright, so this is a copy of the beginning of physical memory. We keep refreshing this until a key is pressed, so you can see it evolving in real time. You can see that there is a field that is constantly updated with a new value. This is a BIOS clock. This value is incremented every time a clock interrupt occurs. This is 18.0 0.2 times per second. If I press any key, it returns. Oh, I forgot. Yeah. The key I press is inserted in editor, because this function only checks if there is a keystroke waiting in buffer. I need to read it out from buffer so that it does not land in my editor. Alright, much better. And also, when the BIOS function waits for any key, not every key is any key. I can push Shift or Control or Caps Lock, and this does not end up my program. And you can see there is another field in memory that lights up when I press Shift. Now I am pressing left Shift. And now I'm pressing right Shift. And now I pressed Caps Lock. And in fact, any program in DOS could write to this memory just as well and modify clock value or modify that bit that indicates that caps lock is switched on, and it would fool BIOS into thinking that caps lock is indeed switched on. As for the context of very beginning of memory, the upper part of the screen, it's the interrupt table. In real mode, interrupt table was always at address 0 in physical memory. It could be moved in so-called unreal mode, but that is a separate story, not for now. Interestingly, my DOSBox stopped responding. Oh, okay. This was something in my Windows, not in DOSBox. The keystrokes were not sent to DOSBox properly. So now perhaps we could, I don't know, modify some interrupt vector. first entry in interrupt table is going to refer to interrupt 0, which is exception 0, division by 0. So we can try to replace this value and set up our own division by 0 handler. We need to set up it as a full real mode var address, segment and offset. And let's divide by 0. This should display a single character. And well, this time we managed to hang the machine completely. As you said earlier, crashy. Well, my mistake was here. Oh, you see, I'm so used to 32-bit Word that that I use offset 4 without thinking, and in 16-bit Word, offset 2 is more natural. This time it works, and it displayed exclamation. So indeed, our division by 0 was handled. But this program does one very evil thing. It replaces the entry in the table, but then returns to DOS, leaving the table modified as it is. So now if another exception 0 happened in DOS, it would jump to this address, but our program is no longer there, because it was terminated by DOS and possibly replaced by something else. This is one of the perhaps more mild demonstrations why giving any program access to all physical memory is in fact very dangerous. Because DOS doesn't know that program has messed with some basic BIOS structures in physical memory. So DOS is not able to revert the changes because it does not know about them. The program is not controlled in any way. So traditionally in DOS, of course, any program could mess as much as it wanted, but it had to restore everything back to order before returning back to DOS. In this case, we would need to store the vector somewhere else, and then when ending the program, restore the vector. Why do I not do this? It's not possible, there is no such instruction. Segment registers can only be used with mov or with pop and push. With one exception, that you cannot do pop CS, which would be useless anyway. Now let's make a place where everything is going to be restored before going back to DOS. Just in case the program uses DS for some other purposes, let's not assume that it has value 0. Let's set it up again here. Or perhaps this way. Well, yeah. Pop CS. Well, I encourage you to try to design a program that would make use of pop CS in any practical way. Keep in mind that it would modify CS register without modifying IP register. Okay, so this is the same program, but this time it at least cleans up before going back to DOS. Alright, this should be called a bit differently. This is no longer memory copy.